introduction. Thank you everyone for being here. I come from the University of Bozen-Bolzano. I'm from the Electronic Devices and Materials and Physics group from the Faculty of Science and Technology. And today I'll be talking about the work that we did regarding upcycling or recycling polyethylene terephthalate PET for the circularity economy. Great. So this is the outline of the presentation, and we will be seeing the introduction for the topic of flexible electronics, motivation behind this work, the fabrication technique that was used to develop the temperature sensors, and the results obtained, and the conclusions of future work regarding this project. As you can see here, we start from garbage, so plastic bottles that were used to develop the substrate, then fabricate the sensor, and test it in a real lab application. So we'll start with describing what consumer electronics are, and these are devices that are very convenient for our current usage on many of the applications that we have these days. Since they are lightweight, they can be stretchable, conformable to any surfaces, and they can be transparent depending on the application that you need it for. They're also good for the integration of different circuits in small areas, and for the industry, they are nice because they come with local processing, and you can easily scale up and fabricate in large areas. Now, this is a 2019 market snapshot of the consumer electronics market. And as you can see here, most of it is taken from flexible displays, the ones that we use in foldable phones, laptops, and so on. Followed by flexible sensors that we see a lot of them, like flexible pressure sensors, flexible temperature sensors that are used widely these days. And the rest of the market is by an upcoming trend of flexible photovoltaics, also e-textiles, which is very important, batteries, and OLED lighting. In 2019, the market was at $37.10 billion, and by 2030, it's expected to grow to $74 billion. Some of the items that are driving this growth can be seen in the smart tags or RFID tags that we see in like tickets to take the train or in bookshelves to keep track of things. Again, smartphone display, smart textiles, and sensors either for robotics or industrial applications. Now, the main drivers or areas that are driving this growth are mainly healthcare as number one, e-consumables as number two, followed by energy, aerospace, military, automotive, and Internet of Things that will be growing significantly since every day we're integrating more and more interconnection in our homes, cars, and so on. Now, this drive in these products can also drive pollution. So that will become an imminent problem at some point because every one of these devices has to be disposed at some point. They cannot work for eternity. So we have to start thinking about how we can reuse them or recycle them to don't impact the environment too much. There's a snap. Okay, so here is just an example of actual consumables and how long they take to decompose in nature. So a carton of milk can take up to 5 years. An aluminum can from Coke or beer can take between 80 to 200 years to decompose entirely. A plastic bag from the supermarket can take 10 to 1,000 years to finally degrade. Plastic bottles can take from 450 to 1,000 years. And the worst of all is styrofoam that it can take from 500 years to never. It's why it's forbidden in some states here in the United States, for example, like New York. And the impact of all this can be seen in our oceans, everywhere in the streets, everywhere where we walk, and in extreme environments such as Antarctica or the Everest, where microparticles of plastic have been found already. So it's everywhere in the world. Now, one specific plastic or polymer that is widely used is polyethylene terephthalate or PET, thanks to its nice properties. It can be extruded nicely, it can be formed, blow molded, but also for consumer electronics, it shows very good characteristics since it can be translucent, almost transparent. It is flexible, very low cost, and it is very conventional since it can come in many shapes. Here we see threads of PET, but it can also come in films and any shape that you have. So for this reason, we chose this popular material to see if it can be used and recycled and be used for consumer electronics on recycling. Now, To prove the concept of circularity, we on purpose use plastic coming from plastic bottles to develop a substrate, fabricate a temperature sensor again, that can be used to measure the temperature in commercial beverages bottles to prove the circularity. So from a bottle, let's develop a device that can measure the temperature of a bottle. The way we did this was by chemical recycling of the PET. So there are two types of recycling, chemical and mechanical. Mechanical is more popular right now, but it's slowly decaying because the material itself loses its properties, and there's a limit amount of times you can recycle PET mechanically. So for this reason, we chose the chemical process where we took a bottle. Actually, the one you're gonna see here, I drank a Coca-Cola in the morning, and that's the plastic I used to develop the substrate. And after that, I chopped it into small pieces of approximately 5 by 5 millimeters square, and washing acetone to remove any impurities or glue from the labeling of the package to have as pure of a plastic as possible. After that, you mix it with fluoroacetic acid and dichloromethane in a 1:2 ratio to depolymerize the PET. Basically, the polymerization consists in taking the long polymer chains and create monomers out of it. In the end, we end up with this translucent and viscous liquid that can be shapeable and moldable, and it remains liquid during the depolymerization stage for a very long time. The advantages of this, again, is that in theory, we're creating virgin plastic with it, so properties are not lost. We break the polymer into monomers molecules. The integrity of the material is not lost, so the plastic will be strong once it is fully recycled, as strong as it was before, and it's a viable solution to the recycling problem that we have these days. Now, upon the polymerization, we have to repolymerize again to create the plastic that we want. So for the repolymerization, we take the viscous liquid that we created, that the plastic is contained there. Then for the specific purpose of improving electronics and the temperature sensor, we spin coat it for 5 seconds at 50 revolutions per minute, and it yielded a film that was on average 64 micrometers thick. After spin coating it, we submerge it into an unsolving induced phase separation bath that consists of DI water, ethanol, and polyethylene glycol to bring the plastic back or solidify everything at once, like freezing it. Now, this is the result, fairly transparent film, but one problem that we saw is that it has some wrinkles or warpage on the surface. This is because of the spin coating process, because when you spin coat the polymerized polymer, the molecules, they don't align. And since you are kind of like freezing it, when you are polymerizing it, the molecules are not aligned, creating this waviness on the surface. However, the waviness in the microscopic level didn't create a big problem for our purposes, since we can see here a very smooth surface with low roughness. So even though we found the surface warping, we created rectangles that were 36 by 23 millimeter in area. So the surface didn't show any discontinuities. It was electrically insulating, keeping the same properties as rigid PET. And the roughness, as I said, it was very small, around 8.96 nanometers, so perfect for thin-film processing. After that, we created the temperature sensor by following conventional thin-film processing techniques. In this case, we put the substrate under vacuum and structured the temperature sensor using a shadow mask. So we took the film, put it on a surface, put a shadow mask, press it. It helped a lot because it evens the surface even more. And we deposited by means of E-beam in vacuum, 10 nanometers of titanium, and by thermal evaporation, 100 nanometers of gold. Titanium was as an adhesive layer to deposit the gold on top. Here we see the structure that was given to the temperature sensor, and a micrograph of one small area of the sensor, indicating that the warpage in the surface was not that significant for function. Here we see, this is random, but this is real here, how we, the idea that we had to put it in the bottle to measure the temperature of the liquid inside. But before that, we did it in an environmental chamber, and we see a fairly linear curve with where we went from 5 degrees Celsius to 65 degrees Celsius instead of 2 degrees per minute to calculate the temperature coefficient of resistance that turned out to be 0.002. And we also detected some hysteresis when going from 5 to 65 and 65 to 5 again. Finally, we tested it in the real life application, where we put it in a bottle here. We pour water at 70 degrees to see how accurate we can measure the temperature. But remember that we are filling the bottle with water, so that there's conduction between the water, the first PET layer from the bottle, the second PET layer from the sensor itself, then the titanium layer and the gold layer. So in the end, when we pour the 70-degree water inside, we end up reading 50.3 degrees from the sensor itself. Of course, it was just a quick experiment. It can be fully optimized and get more accurate results with further research. So in the end, to conclude this work, we found that we can use this chemically recycling technique as a viable solution for the plastic problem, and not necessarily create more plastic and throw it in the world, but reuse what is already here and develop a platform to keep using the plastic that is already here to reduce the impact, because this field will be increasing very quickly, and we're going to be seeing a lot of devices everywhere soon. So we also found that there's a very large scale potential of this technique, since you're melting the plastic and you can give any shape that you want. And there's also opportunities for optimization and develop commercial applications with this technique. For future work, we're looking to enhance the properties. Here's just an example of what can be done. We can embed oriented fibers to create composites using the plastic as polymer matrix to enclose oriented fibers to increase the mechanical properties of the material based on the application that it is required for. Also, we have to calculate the response and recovery time of the sensor, because we focus more on the substrate, and keep developing a great platform for thin film electronics using also other materials that are even healthier for the environment, to the point that they can actually treat the environment as they decompose. Okay, thank you very much.